section 11.1, infinite sequences and series. I'm going to keep moving forward. I had you watch a video online from our college algebra course, just so that you're familiar with the concept of what a sequence is. We're going to dive a little bit deeper into sequences and series. Well, I should say quite a bit deeper than we do in our algebra classes, obviously. But also keep in mind that this is like just your first glimpse into a very big and important topic in mathematics. Those of you that are full-blown math majors, not even pre-engineering, but if you're a math major, in particular, I think the math for secondary teachers, it's an elective, but there is a course called intermediate analysis that we teach here, which is like basically advanced calculus. It's, you take Cal 1, Cal 2, Cal 3, then intermediate analysis is upper level mathematics, 4,000 level mathematics, lots of proofs and theorems. So a lot of what we will do in chapter 11, we will learn the techniques, and I will say this is how this test works. When I say a test, what I'm talking about are tests for convergence. So when we talk about sequences and series that are infinite, we're going to be wondering what happens to them as you go out towards infinity, as n goes to infinity, or as the number of terms in your sum in your series goes to infinity. Does it converge to something, or does it diverge? And we're going to have lots of tools to be able to answer that question, but the proof that those tools work is not what we talk about in here. We just use them. In analysis, we prove them and even develop new tools and handle even more complicated sequences and series. Okay, so today we're going to be doing just sequences, and then next time we're going to move on and spend most of our time on series. Okay, series are sums. You're adding things up. Sequences are lists. Sequences are lists, series are sums. So let's define things. Let's start talking about what we mean by convergence. That's what we need to know today. And I need to take my jacket off because it is warm in here. Are y'all warm, or is it just me? I'm just overdressed, aren't I? All right. A sequence. Oh, do y'all want me to broadcast? All right. A sequence can be thought of as a list. Sorry, a little typo there. Thought of as a list of numbers written in a definite order. And the notation that's commonly used for sequences is this subscript notation. So a sub 1, a sub 2, a sub 3. By the way, for the next 2 or 3 sections, we're really leaving behind things like derivatives and integrals for calculus. Where this is still calculus is the fact that we're talking about going to infinity, which revolves around limits. We need to have limits to do this. And so anything that involves limits is calculus. I think I may have told you this before. The first day I walked into my calculus class here at Wayland, the thing that was on the board that Dr. Alms had put up there is limits is calculus. That's what calculus is all about. So anytime you are talking about taking it to the limit, take the limit, then we're talking about calculus. So that's why this fits in here, even though we're not going to be talking about derivatives or integrals. We're going to be talking about lists. Now that's informal. The formal definition in mathematics is also important because it gives us the tools we need to prove things about it, is that a sequence is any function whose domain is z plus or n. These are the positive integers, or sometimes called natural numbers. Okay, so in mathematics, a function is a thing that takes inputs and gives outputs. It's well defined so that one input always gives you one output. Now, when I say the domain is the integers, that means that you've got a function like a that depends on something, maybe n, and that function a maps, and this is some notation that if you've had proofs you will have seen. If you haven't had proofs, we may not see it as much in here yet, but you will in some later math courses. All I'm saying is a is a function that maps, meaning takes as input in and turns them into real numbers. So a is a function that maps the natural numbers into the reals. In other words, it's only defined at 1, 2, 3, 4, 5, 6, and so on. There's no a of 1.5. It's just a of 1, a of 2, a of 3. So the only inputs are going to be n, where n is an integer, a positive integer. Okay? But instead of function notation, oh, actually, I have this. Don't write that. I didn't realize it. It's right here. And instead of writing in function notation, we use subscript. Okay? So a of 1 is written as a sub 1. So when you see a sub 1, that just means plug in 1 for the value. And the sequence, if I want to describe a sequence all at once instead of listing out the terms, I will sometimes use this notation. You put a curly brace, a sub n, curly brace, as n goes from 1 to infinity. That's the notation I'm going to use to describe a sequence. And what's inside here is the function. And this just says where my n starts and where it goes. So that's the sequence as of a sub n as n goes from 1 to infinity. Or just, sometimes I'll leave off the 1 to infinity and it's implied. So when you see something written down here like these examples, notice that what's inside is just your function definition. It's your formula, right? So in this case, writing the first 5 terms just means plug in, right? What's the first 5 terms of the sequence n as n goes from 1 to infinity? Duh. 5, dot, dot, dot. The first 5 terms of n over n plus 1. This means plug in n equals 1, then 2, then 3, then 4, then 5. So 1/2. Comma 2/3, 3/4, 4/5, 5/6, dot, dot, dot. This is going to be a common thing you see a lot in this class going forward is the dot, dot, dot. That means continue on in the same pattern. Okay? Like the ellipsis, not ellipse, the circle, but the ellipsis from your English class. And there's no difference between 3 dots and 4 dots. It's just me being sloppy. Sometimes there may be 2, there may be 7, I don't know. But dot, dot, dot. Keep going in the same pattern. All right, so in this one, I've got a formula inside here that is negative 1 to the n times n plus 1 over 3 to the n. Okay, so you can either do this in your head or you can come off to the scratch paper. I'm going to come off to the side here just real quick, just so you can see for the first couple of terms, what does this thing do? If you have a negative 1 to the n plus 1 over 3 to the n, and you plug in 1, what do you get? Negative 1 to the first times 1 plus 1, or 2, over 3. So what does that negative 1 to the first become? It's just negative. Negative 2/3, right? Now on top, I'm just adding 1 to whatever my n is. So on my second term, I know I've got a 3 up top and a 3 squared on bottom, which is 9. But what happens to the negative 1 now? Negative 1 to the second is positive. So what is that thing doing? What is negative 1 to the n doing to the terms? Changing sign. So it just... Yep. So it's alternating back and forth, and that's a word we'll use a lot later on too. It's an alternating sequence because it changes sign. The next one's going to be negative then, and it'll be what? 4 over 3 to the third, which is 27.
Do we reduce these if you're in...
Yes, you should. So yes, that one is actually 1/3. So my final answer, I should probably write that as...
I was just wondering.
Yeah.
You can't really see the pattern if you're
Right.
looking at it.
Exactly. But now, if you're given the formula and you're asked to write out the terms, there's no reason to need to see the pattern because you have the pattern in the formula, right? But yes, in this type of question where you're asked to write out the terms, you are encouraged to reduce. That one does not reduce. The next one would be 5 over 81, right? And then 6 over, is it 243? Which actually reduces, by the way. You can take a 3 out of the top and bottom. 2 over 81, comma, dot, dot, dot. Okay, sine of n pi. That would be sine of pi, sine of 2 pi, sine of 3 pi, sine of 4 pi, sine of 5 pi, dot, dot, dot. But this goes back to what actually Kaylin was asking. Should we simplify that?
You don't need to.
Well, if it's obvious that something is much simpler, I think you should. What is sine of pi?
0.
0. What's sine of 2 pi?
0 again.
Wow. Sine of any pi, right? So remember, sine is the y coordinate on the unit circle. So pi is over here, right? There's pi, and then 2 pi, and then 3 pi, 4 pi. The y coordinate's always dot, dot, dot. So notice, by the way, how this sequence is actually that sequence right there, isn't it? It's the 0 sequence. So just because you're given a formula doesn't necessarily mean you've been given the simplest formula either. So sometimes reducing or simplifying helps you see that it's actually a much simpler relation than you were given to start with. I'm going to skip the step of writing it out and just ask you, can you tell me what the cosine of pi is? -1. It's the x-coordinate on the unit circle over here, right? Which is -1. And then cosine of 2 pi is +1. It's the x-coordinate on the unit circle over here, so that's 1. And then cosine of 3 pi is -1. Cosine of 4 pi is 1, -1, dot, dot, dot. Could you write that another way? What would you... Instead of writing it as cosine of n pi, can you think of another way to write it? -1 to the n. And then check that the order works. So plugging in 1 does give you -1, so that's right. Sometimes you might have like a +1. If this had started at 1, -1, 1, -1, you could put a +1 up there. But anyway, the point is now this is the same sequence. Okay, this extra, I didn't ask for that in the homework or in the exercise here. I did just want you to see that these two sequence definitions are the same sequence as these two sequence definitions. Okay. Sometimes we can actually describe a sequence without a formula and still talk about it. I've got two examples here. One where I don't give you a formula at all, and the other one I give you what's called a recursive formula. Let's talk about the sequence whose nth element is the nth decimal of pi. Okay? So what is that sequence then equal to? Do you remember pi? So what's the first decimal place of pi? 1. 4, comma. And so on, right? Just either pull it up on the web, pull it up on your phone, put it up on your calculator. 1, 4, 1, 5, 9, 2, 6. That is a sequence because it is an ordered list. In this case, it turns out to be a sequence that does not converge. It forever bounces back and forth around, has no repeating pattern. But it's still a sequence. And I've just described it in another way. Okay? Do you recognize this sequence? Have you seen this before? And this should say 1. I'm sorry. Make that a 1. That was a mistake. I just recognized it. F1 is 1. The first element in the sequence, 1. The next one is 1. And after that, you just keep adding the previous 2 together. So it would be like 1, 1. The next one, F3, would be F2 plus F1. So 2. F3, we did F4. Now is F3 plus F2. So F3 plus F2 is 3, and then add the previous 2. Add the previous 2. Previous 2. 21. Have you ever seen this sequence before? It's got a name. Actually turns up in a lot of places in the real world, even in biology in particular. The name doesn't, but the sequence does. If you start counting things like the squares and the spiral on the outside of or the diamonds on a pineapple, or the number of offshoots, leaves coming up off of a stem, or if you look at a pine cone and you look at the different diagonal patterns there, they all tend towards something called the Fibonacci sequence. A lot of good, interesting things about the Fibonacci sequence that I'm going to skip over for now, but may come back to later on. I got a video to show you. Maybe we'll do that at the first class next time. Okay, so sequences are lists. Plugging into formulas, that's not hard. You guys can all do that. One thing I just want you to think through is how would I draw a picture of what a sequence is doing over its list of terms. One way to visualize a sequence is to plot on a line. So this particular example you have here at the bottom of the page, both of these are visual representations of this sequence B up here. Notice what I'm doing is I'm plotting at 1/2, and then 2/3, and then 3/4, 4/5, 5/6, and so on. So then, that if you come and get closer and closer and closer as you go towards infinity, what's happening to that sequence? It's approaching or converging to 1, exactly. Now you can also see it vertically, right? So if you come and you look up here at the plot, what I'm actually doing is I'm plotting this the same way I would plot a function, except remember that as a function it's only defined at your integers. So it's only defined at 1, 2, 3, 4, and the same way that you would with the function, you plot the height of the curve. Okay? So this is 1/2, 2/3, 3/4, 4/5, 5/6, sevenths, and so on. And what's happening to the height of that thing? As you go out towards infinity, you are converging. That's what you get when you plot on the plane. It's just two different ways to look at what's happening in your sequence. Now, in both of these cases, as you see them, they're getting close to something, and so we want to talk about what it means to converge as a sequence. Right? I mean, informally you can say it looks like it's getting close to, but mathematically we need something better than what it looks like. So, convergence of a sequence, we're going to come up with our formal definition to be able to use in the same way that there was a formal definition for the limit. There's a formal definition for the limit of a sequence. When we did limits back in Cal 1, hopefully you learned something called the epsilon delta definition of the limit. I'm going to give you an epsilon n definition for this limit. We say a sequence converges, and again, this is the informal way of describing it, if the value of the sequence gets arbitrarily close. What I mean by arbitrarily is as close as I want it to some value when the index, which by the way is the name of the subscript. I call this down here the index. Is sufficiently large. Okay? So let's think about what that means in looking at this. Now, we made the claim on those pictures above that the value of the sequence was getting close to 1 as n went to infinity. Why is it the case that this is getting close to 1? Well, let me say it this way. Why? The value of n over n plus 1 is as close to 1 as we want for a large enough n. So for example, let's say I tell you that I want you to be within 0.0001 of 1. I give you a number and I say, get that close. Can we get that close? And the answer is yes. We just got to take n large enough. Just keep going until n gets big enough. Once you're past a certain point, all of the sequence will be within that range. And if I want to get even closer, I can do it. I just got to take a bigger n to get there. So mathematically, to prove something converges, you got to prove that that's always true. That no matter how close you want to get, I can take a big enough n to get that close. Okay? And that everything past that n is within that range of your limit. So that's the same idea that we've talked about before with limits. We now are just going to do it in terms of sequences. I'm going to pause the recording. What does it mean to say the limit as n goes to infinity of a sub n is equal to L? Notice how it looks very similar to that limit, except we got a couple of extra nuances. Namely, it's going to infinity, and it's also a sequence. So here's the formal definition in mathematical notation. For every, and I'll write this again in your notes, for every epsilon greater than 0, there exists a capital N. Notice how there's not a delta now. There's a capital N. That capital N can depend on epsilon. So the smaller the epsilon, usually the bigger the n. Which is out of This means is an element of. Notice it's not the backwards one that I've got written up there, but it's a forward one. This is an element of, and I'm going to use this notation. You recognize that symbol? I've written it in the notes already once today. Integer. Positive integer. Natural number. I use n because it stands for natural numbers. That's your digits, your counting numbers. 1, 2, 3, 4, 5. It's the first set of numbers we ever discovered as human beings, okay? When we started counting things, we started using natural numbers. So there's a natural number out of, or there's a capital N, such that A sub n, actually I'm going to write it the same way I've got the one on the board. Don't write that. I'm going to say n greater than or equal to capital N implies that A sub n minus L is less than epsilon. So what's different about this symbolic notation from what's on the board that I talked about, or from the previous definition of limits? One difference is we're not talking about deltas. We're talking about capital N's. And we're not talking about delta being within some range of the limit. We're talking about every value of little n bigger than capital N. And this will make more sense with the picture down here, but let's write out what these actually mean, okay? So this says, for every epsilon greater than 0, that's the first statement, right there. And then all of this says, there exists a natural number n. So I'm going to make that a little bit longer. The actual number n, depending on epsilon, such that n greater than or equal to capital N, that's this piece right there, implies that A sub n is within epsilon of L. For every epsilon greater than 0, there exists a natural number n, depending on E, cap n, such that little n greater than or equal to cap n means that A sub n, now notice this n here is this n here, when the subscript is big enough. So, in other words, when you're far enough out in your sequence, you're close enough to L. So look at these two pictures that I have underneath here. Let's say this is my first sequence right here. Don't draw the line that I just drew. I didn't mean to actually draw on there. I'm trying to drag this along just so you can see. This represents the height at 1, 2, 3, and so on. But what appears to be happening as you go out to infinity? You're getting closer, okay? Now, in order to say this actually converges at infinity, what that means is you need to be able to choose any epsilon. So let's say I take and choose this epsilon right there. Okay? That distance from the center out to the edge is epsilon. Okay, so I'm going to do is I'm going to draw a horizontal line as best I can. That's supposed to be very straight. Okay. So I picked an epsilon. Is there a place that I could go to and draw a vertical line and say that every element of that sequence past that line is inside that interval? And I can, right? Maybe right about here. That's the end that I'm talking about. From this point forward, all the sequence is inside. It's a very abstract, conceptual, trying to lay down the foundation for what we mean when we say that any sequence, no matter what it looks like, converges to L. This one would converge to L if I could say that no matter how small, whatever epsilon I choose here, there's some n, so that past that n, all of the sequence is inside that range. And if I choose a smaller epsilon, there may be another n further out. But it's still out there that I can get that close. Okay? That's what it means to converge. Same thing on this one. If I drew the line, let's say put the epsilon right here and right here. So this distance right here, I'm going to call epsilon. Now choose whatever epsilon you want and try to draw those lines horizontal. Then look at your picture and say, where's the point on this axis here that goes with this epsilon so that past it, everything's inside that range? I can't go here. In fact, if I do anything before here, I got a problem because that's outside. But once I get to here, that one worked. And if you drew yours closer, you might have that your end had to be further out. It's just wherever's the last place where you've got a point outside there. Okay.
So the rest of it is just after the line.
After the line, I found the place. Okay? After here, that is for n greater than or equal to cap n, a sub n is between L minus epsilon and L plus epsilon. All the sequences inside there.
You can bust your epsilon wherever you want.
Well, it's a little bit more complicated than that. What I'm saying is this has to be true no matter what epsilon I choose. So what I'm showing you now is just a visual to help you understand what the notation means. I've not given you a formal proof of this. I've not given you a single sequence example that you can actually prove with a mathematical proof that this limit converges. In fact, we're not going to do that in here. I know you're disappointed to hear that I'm not going to make you prove things on this test. But the point I'm trying to make here is that you understand that the concept of convergence means no matter what epsilon I choose, there exists an n. So if I were to want to prove this mathematically and formally, I'd have to show that no matter what epsilon there is, there's an n that I can find. Usually that involves finding a formula for n, depending on the formula for your sequence. Okay, and I don't want to go down that road. Here's another way to think of it. I like to think of it as the Epsilon Endgame. I've called it the Epsilon Delta game for this guy over here. Think of it this way. Player 1 picks any epsilon, as small as they like. Player 2 has to find the integer n so that all the points after a sub n are inside that range. If player 2 is always the winner and is guaranteed to be the winner, then we say the sequence converges. If there's ever a time that player one wins, then the sequence diverges. Now, I don't have one on the screen here, but here's an example of one where player one would lose. Oh, I got to stop here. Let me draw this picture. Imagine my sequence -1 to the n. Okay, what does that look like when I graph -1 to the n? At 1, it's -1, right? At 2, it's +1, -1, +1, -1, +1, -1, +1. Okay? So let's say we claimed this was L right there. Now, here's the thing. If I chose my epsilon, player one says, oh, my epsilon's this big. Player two wins. Because all player two has to do is say, well, here's my capital N now. If I just go from here, everything past that point is inside that interval, right? Now, what if player two was meaner than that and said, sorry, player one said, here's your epsilon. Right? Here's the range you have to be inside of. Is there ever a place that I could go to far enough out so that all the red dots end up inside here? The answer is no, because there's always going to be another red dot outside. So this one diverges because there's always a red dot outside for some epsilon. A big epsilon was okay, but player one chose an epsilon so that player two loses. If that's true, if player two loses, then he's divergent. Okay? The next question we're going to come to, and this is where I'm going to break off, is how do we actually determine whether these sequences converge, like these limits down here, and what do they converge to? All right, so we'll see you Sunday night. Y'all have an excellent weekend, and we'll do our test on Monday. So, don't I, have 50 minutes from last class?
Did we
You canceled on us. We didn't cancel on you.
Yeah, we didn't cancel on you. You canceled on us.
I mean, technically, that's 50 minutes on your side, right?
I gave you 50 minutes.
That's $40.
I let you out
tuition,
50
and we're not
minutes
gonna do
early.
that. $40 in tuition. I won't.
Instead of having the learn calculus like that, you swing some more. Let's just kind of stuff.
Problem was, I was already awake at that point.
Well,
I
I
just
had
sat
a
there.
8 a.m. So.
Yeah, I did too. Sat there and did nothing for an hour.
But no, that's what I did. I literally got up, went to my day, and then went back.